recording. That's important. Sharing my screen. Good. All right. So let's just do a little bit of review before we do this this confidence interval, which oh, whoops. You know what? I always forget to do that. But just mute everyone. Hopefully not myself. That today would be that day. Okay, there we go. Or maybe it's for the best. So before we go through and do this confidence interval, which I released you to do on your own, we'll do it together, of course. Let's just have a little bit of review, and maybe I'll bump this page just so it makes more sense to me. There. Okay. So a little bit of review. When we're analyzing one or two samples of numerical data, now so far we've only seen one sample, and then today we're going to move into a special case of two samples, and then on Tuesday I'll do two independent samples, which are two proper samples, which I'm not going to put on the test. So up to the end of today is what's on the test, and I'll make a note of that. Because I don't like to introduce something on the Tuesday and then test you on it on the Thursday. That's crazy. And so it will, of course, be on the final, but not on test 2. And so let's see here. To analyze one or two, which we haven't seen yet. That's why I'm putting it in brackets. One or two samples of numerical data, we use the t-distribution. The t-distribution, which is what we talked about quite a bit last day, right? The t-distribution is very similar to the normal distribution. In fact, it's got the same shape. It's centered on 0. The only thing is that the shape itself depends on your sample size or your degrees of freedom, right? And so for small sample sizes, it just says, hey, I don't know very much about this population, so I'm not, willing to attach very small probabilities because I don't know. And then as you increase your sample size, your degrees of freedom also increases, and it approaches a Z distribution relatively quickly. And so it's not something to worry about, but it does introduce that sort of new table that we've already been using. And so the t-distribution relies on the degrees of freedom. Which we saw in the chi-squared case as well. So the degrees of freedom happen in a lot of test statistics where the shape is determined by some value, some degrees of freedom. And so we don't need to worry about what degrees of freedom are because it's beyond the scope of this course. For us, we just need to know, how do I calculate it, right? We don't need to worry about what they are. Okay, if you want to know what they are, you can take a couple of years of stats and then you'll find out eventually. So then, and maybe even then, it took me a long time for it to click. Oh, okay. As long as you know how to calculate it, you're fine. Okay. Sample size -1. That's for one sample mean. Now that's on your formula sheet, right? This is for one sample mean. And so if you've decided that you have a one sample mean type of question, then that's your degrees of freedom. But of course, it's on your formula sheet. And in terms of, let's see, where's our formula sheet? Here. right? One sample mean looks like, oh boy, where is it? Here. I have the degrees of freedom down here at the bottom, only because we use it not just for the critical value in the confidence interval, right? Then we need to use the same degrees of freedom as we do for the t-test, right? Which is here. And so overall, the degrees of freedom is n minus 1. Okay, so for our hypothesis test, we said that the null hypothesis is that mu is equal to mu naught, right? Where that mu naught is the same thing that we saw in the one sample proportion case. I just have one sample. I can't compare it to itself. That'd be weird. And so then I need to compare it to some value. And so here I'm going to say where mu naught is the value we want to compare our sample mean to, is the value we want to compare x bar to. So that's from the question, right? In the example that we did, we wanted to compare the mean dissolved oxygen level to 5, right? We were concerned that it was less than 5, and turns out it wasn't, whoop, whoop, which is good for the fish, right? And so that was good, but that's where we get this mu naught from, is from the question. Okay, then you calculate your test statistic. I'm not going to write the alternative hypothesis because the sign is the only thing that changes, and that depends on the question. Do you want to know if mu is less than mu naught, greater than mu naught, different from mu naught, right? And so I won't write that down, and that's also the setup here on your formula sheet, right? But then we calculate our t, which is our test statistic, which says, okay, how far is my sample mean from my hypothesized value, right? My hypothesized mean, taking into account the standard error of x bar. What's really nice about means, mean questions in general, is that the standard error stays the same regardless of if you have a confidence interval or a hypothesis test, which was not the case for proportions, right? Then we had to change it up. You follow the formula sheet and then you're fine, but then we had to change it and be really aware of that. But here, the standard error of x bar is always just s over root n. So that's nice. Okay, so then we said, all right, we calculate t as x bar minus mu over s over root n, and then we take that t and we use it to find the p-value using the t-table, right? And so to find the p-value, we use the t-table. What's really nice is we've already been using the t-table to find p-values for our z's, right? So now the only thing that changes is you're not on the z star line anymore. Now you're on whatever degrees of freedom line, but you have those skills already and those techniques. And so we're just building on that. And so now we use the t-table with n minus 1 degrees of freedom. This is where I want to make a note, because it's kind of a common mistake that I see. If the exact degrees of freedom is not on the table, right, then you're going to round down, right? And so if the exact degrees of freedom is not listed in the table, we must round down, right? We must round down to the nearest degrees of freedom. Obviously, that is on the table, so I'm not going to write that. To the nearest degrees of freedom. Why is that? We know that as we increase our sample size, our point estimate gets more and more stable. It becomes closer and closer to our population mean, which is what we're trying to estimate, right? And so our degrees of freedom is linked to our sample size. If I say, oh, I have 1,000 degrees of freedom instead of 100, that's claiming to have a sample size of 1,000 instead of 101. And so then you're claiming to have more reliable results than you actually do, and that's really bad, right? And so if we go to the table, we'll see there's no real difference in the values. We'll use 100 later. All right. Here at 30, it stops being exact, and 40, 50, 60. So even if you're choosing between these two, right, you'd have to bump it down to 100. But notice if you compare the values across here, there's really no difference, right? And obviously, if you're using software Excel, for example, then it can just take any degrees of freedom. On the assignments, though, when I get you to follow up with the exact degrees of, or p-value, right? Just for practice to see that, okay, it exists and I can find it and it is in that interval. I think I say to use the same degrees of freedom as you used in the table, because otherwise there's a chance that they don't match up, but pretty low chance, but still. Then, once you have your p-value, you're off to the races, right? That conclusion. So then the p-value, the one-sided or the two-sided p-value, let's just recap our conclusion just briefly. If the p-value is less than alpha, we have enough evidence to reject H naught. Of course, you're going to say what your p-value range is, how does it compare to your alpha level, whatever it is, right? So you're going to be more explicit, but the general rule is always going to be that if the p-value is less than the alpha level, we have enough evidence to reject H naught. In favor of HA, but I'll just write reject H naught. And then, of course, if the p-value is not less than the alpha level, then we do not have enough evidence to reject H naught, right? Always has to be in terms of H naught. I will take marks off, not marks, half a mark off if you state your conclusion in terms of HA, right? You don't even mention the alternative hypothesis. All your conclusions are about the null hypothesis. Why? Because we did all our testing assuming the null hypothesis was true, right? We assumed that the center was in fact mu naught, right? Which is our null hypothesis that mu is at mu naught, right? And so that's why we have to either reject H naught or fail to reject H naught, and those are your only two options. That was essentially a quick recap in just hypothesis testing in general, but it's that time in the term where that's beneficial. Okay, so let's see here. I want to add a page so we can do this one. So I asked you to calculate and interpret this on your own, but now we're going to do it together so you can check your work. Here we go. Business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada, OSB. Included in each report are the assets and the liabilities the company declared at the time of the bankruptcy filing. And so a study is based on a random sample. We love seeing that. Why? Because then we can assume that these reports are all independent of each other. That's a good thing, right? That's one of our conditions. And so, and we also are given that N is 75 from the current year. And so the average debt, which is the liabilities minus the assets, is $92,172. What is it? So this is from the sample, right? And so here, this tells me that X bar is 92,172. With a standard deviation of 111,538, huge spread, right? We're not going to mention it, but when the spread is larger than the mean, it's kind of a concern, but we'll ignore that. We're just going to go for it. This is our sample standard deviation, so it's S, a lowercase s, is 111,538. Hopefully I did it last day. I forgot to do it today. Your first fork in the road is this a means question or a proportions question? Of course, it's a means because that's what we're talking about, but we need to be able to read these things and figure it out. So what's the biggest clue? Probably this. The average and the standard deviation. Those are only things that I'm going to need to give you if it's a means question, right? If it's a proportion question, then I need to give you the n, of course, and maybe the sample proportion or the number of successes, right? So different information for different types of questions. The next clue, if those aren't obvious to you, which is totally fine, then we want to construct a 95% confidence interval for the average debt, right? And so now the average is, of course, the mean. And so then I want to make a confidence interval for the mean, which means it has to be a means question. Okie dokie. Here we go. From our formula sheet, I'll write it on a fresh page here. We have X bar, so a confidence interval for mu is X bar plus minus T star at n minus 1 degrees of freedom. Now, often I don't write that subscript n minus 1. Technically, it should be there just to indicate the degrees of freedom, but sometimes or often I drop it times S over root n. Okay. We have X bar, we have S, and we have N. Okay, little inner city feel here. Hopefully it was just a car backfiring or something. We'll see it on Castanet, I'm sure. Yeah. Yeah, and we were just in here. I don't see anything. The only thing we don't have is our T star, but I think we're feeling pretty good about finding it, right? We need T star. We need T star, which is still our critical value, right? The thing that tells our confidence interval, the confidence level, is always going to be our critical value. And so we need T star for a 95% confidence interval at degrees of freedom equal to n minus 1. I'll do the little calculation here. 75 minus 1 is 74. This probably feels excessive, but when you're writing the test, right, so many little slip-ups can happen. And as long as you tell me what your thought process is, right, then as long as I can follow along and kind of make sense of it and what you're doing is good, then little typos, right? If you told me that 75 minus 1 is 70, that doesn't matter, right? I don't care about that. That's just a weird little hectic math moment, right? And so as long as you follow through with that, that's fine. And so I encourage you to, even though it feels okay, I don't have a window that way, so I don't know, but I feel like it's that way. But there's a crew eating pizza out here, so, and they don't look too concerned. So just follow their lead, I guess. Anyways, feels excessive, but just tell me everything that you're doing, thinking, feeling on the test so I can follow along, right? Now, I happen to know that there is no 74 degrees of freedom line on the table, but that's okay. Hey, get in there. I'm gonna copy this. Oh, you know what? I'll feel so clever if I just do this for once. I never remember to do that. Then I can copy this. Ah, clever girl. Pat myself on the back. I go to my tea table and I'm choosing between 60 and 80. And of course, this is the scenario where I have to bump it down to 60, tempting to go to 80, but then we'd be lying. Can't remember who said it. There's lies, damn lies, and statistics. Anyways, famous quote. This feels special. It's not, but it feels special. It's an even 2 for our critical value. Finally, right? 95% confidence interval. It's actually exactly 2. Awesome. It doesn't matter, but it's a fun feeling. So here, what I'm going to say is, so technically the degrees of freedom is 74, and I'm going to follow it up with, but using degrees of freedom equal to 60, just to illustrate that you also knew to bump it down. But using degrees of freedom equal to 60. T star is 2.000. I'm going to keep those zeros only to illustrate that I didn't do any rounding or anything. It is that value. You don't have to. Okay. Now we have all our components. And so our X bar was 92, 172. Oops. I'll just jot it down again. Compared to 2 sample proportions, these are just itty bitty, right? So kind of nice. 92, 172 plus minus 2.00 times 111,538 over the root of 75. That's another common mistake I see is, so you did all that work for the degrees of freedom, that this formula just has n, right? And the n is still 75. And so you use that 75. Okay, I did unable to load photos, but I need them. Oh, there they are. Is it this one? Nope, it's this one. Yeah. I conveniently did it in my last class. Now I'm really hoping that I didn't make a typo here. I checked it, but you know how it is. 111,538 over the root of 75 times 2, that's my margin of error, right? So I just called that m in my calculations. If you haven't figured out the store function on your calculator, that's going to be really worthwhile, right? Because then you can keep all your decimal places and not worry about it. And so I called it m, but that's the same as storing it in some value. And then we want 92,172 minus m, and then plus m. And my interval, this is money, so we round to 2 decimal places, right? And so here, from 66,413 and 40 pennies up to 117,930 and 60 pennies, rounding to 2 decimal places. Nice. We have to interpret this interval. This is only half the work, half the marks. Uh-oh. Right? And so on the test, I'll have a prompt, right, that says interpret the interval, right? And so that's half the marks, just so you don't forget to do it, because often people forget. But what's our standard confidence interval interpretation? We are 95% confident in this case. The interval from the lower to the upper, so from $66,413.40 to $117,930.60 captures, and I want to see that word because there's no better word for what the interval is doing. Okay, and it's trying to capture the population mean, in this case, the population mean debt. And so here we don't have to think too much about it. Once you have your captures, then you can just reword the question as an answer, right? And so it doesn't matter. Sometimes they sound a little wonky, but we were asked to construct a 95% confidence interval for the average debt of these companies at the time of filing. And so captures, continuing from our blurb, the average debt of these companies at the time of filing. Captures the average debt of these companies at the time of filing. Nice. We did it. One sample mean. But it was also a way to introduce the t distribution. Okay, we kind of lay low today. We're going to do the same thing with a tiny twist. Okay? And so here, I guess this is the end of one sample means, except we keep working on it today. And so now, today, we will introduce a special case of 2 samples, right? So we have 2 samples of numerical data. So today we will introduce a special case of 2 samples of numerical data. That special case of 2 samples is when the observations are paired. So if you imagine your spreadsheet, right now I have 2 columns, right? Sample 1, sample 2, but the special case, so if you imagine your spreadsheet, you have sample 1, sample 2. This is your spreadsheet. Oops, this should be up here. And your observation, right? So your subject 1 gives you information in sample 1 as well as sample 2. Okay? And so now we call this paired data. right? And so observation 2 gives you information for sample 1 and sample 2. Okay. And so now the information in sample 1 and sample 2, they're paired on each observation. In sample 1 and 2 is paired on the observation. Some common examples where we have paired data are things like pre and post scores, right? And so you write a test and then you, I don't know, have some tutoring or whatever, you study, and then you rewrite the test, a different test, but similar, right? And then you look for an improvement, usually, or if there's been a change. And so kind of pre-post scores. We can make a stretch if we have twins, for example, right, where there's no reason to think that there's any difference between sample 1 and sample 2, twin 1, twin 2. I don't know. Our feet, that's a common example too. If you're comparing brands of shoes, it's a really kind of famous one where they studied the different rubber in the different types of shoes. So they had these kids wear one shoe on one foot and one shoe on the other foot randomly, right? And so then we're paired on the child, right? Because how you shuffle your feet and how you move and how much you move, that depends on the child, right? There's some that aren't really wearing down their shoes at all. There are some that really go through their shoes. And so to capture that difference, then we use paired data. And so paired data is section 7.2. And just as a sneak preview, 7.3 is going to be when we have two independent sample means, right? Then I want to compare these two independent samples, and that's very similar to the two sample proportions that we had. Overwhelming because we have information from both samples, but beyond that, nothing crazy. And so two independent sample means. So that's coming down the pipeline next week. But today we're going to talk about paired data. I'll develop it here. It's in the slides later, but so what we said was, okay, if I'm comparing these shoes, right? Then we said, okay, we've got some active kids that are going to go through any shoe faster, right? And then we've got kind of the readers, us readers who didn't really go through shoes at all. And so we need some way to reflect those differences. Haha. So what can we do? Well, I can look at the difference between observation 1 and observation 2. So sample 1, sample 2 for each child, or we are going to talk about the students. So for each observation, and then what do we have? Now, if I've calculated the difference, right, then I have one sample of differences, and that's going to be what we're doing today, which puts us back to one sample means, right? It's just that we're analyzing the differences instead of just the raw data. So an example of paired observations is this one. So 200 observations were randomly sampled from the high school and beyond survey, where the same students took a reading and a writing test, and their scores are shown below. At first glance, does there appear to be a difference between the average reading and writing test scores? Here, we're not used to seeing this, but I would say generally Not really. There's more variability in the reading scores, right? The writing scores tend to be more condensed and slightly higher median, right? And so, but there's still a lot of overlap. And so that's what we're going to compare. Now, if I asked you this, right, how we decide to use paired data instead of just two independent samples, right, is okay, if a student has a high reading score, do you expect them to also have a high writing score? Probably, right? And so we want to capture that. Whereas if a student has a low writing score, then we suspect that they'll probably have a lower side reading score, right? And so there's that that pairing that we need to take into account. And so our observations might look like this. And I'd say the tricky part about talking about two samples is we need to decide if I need to condense it into a paired data situation or just treat them as two independent samples, which we could do. Okay, but in this case, we don't want to do that. We want to capture the fact that someone with a 57 in reading also got a 52, which compared to the rest of the scores is quite high in the writing as well, right? And so on and so forth. Wow, look at this one. Kind of an anomaly here. Doesn't matter, we're going to analyze it. Okay, we're still analyzing if there's a difference in the reading and the writing scores, but we also want to take into account that we have strong students, weak students, and we don't want to just mash them up into two individual groups. We want to capture that. Oh, I guess, yeah, no. So what we do, once we've decided that we have paired data, then we calculate the difference. The order of how we calculate the difference doesn't matter, okay? And so to analyze paired data, we look at the difference of the pair of the observations. And here I'll say, or write minus read. It doesn't matter as long as you're consistent. How you calculate your difference. You can't go from one minus the other and then all of a sudden halfway through calculate your difference, because then it doesn't mean anything, right? A positive difference in this case, if we use read minus write. Now for me personally, I always do the first one minus the second one because otherwise I get confused. And so we make a new column of differences. Okay? And so now here I have one sample of differences, which is great because that's back to one sample mean, right? I have numerical data, differences. The only thing is the interpretation, right? And so we'll focus on that. But in terms of our calculations, you don't even really need the paired data section on your formula sheet. I put it on there just so that you can kind of focus, right? But you don't need it because you just go back to the one sample mean situation. So we calculate the differences. A positive difference in this case, right, means that the reading score was higher than the writing score, and a negative difference means that the writing score was higher than the reading score. Okay. We can also make a histogram. I'll mention this because we'll talk about it in the conditions later. But one of the conditions is the normality condition, right? And so one of the things I can do is I can make a histogram of the differences, make sure they look approximately normal. They do. So the normality condition is met. Also, because our sample size is 200, that's more than 30. So I'm already allowed to assume normality, right? But it's nice to see it in action there. Okay. The thing we want to, Please stay on the line. The thing we want to learn about is the average difference between the reading and the writing scores of all these students, not just the sample that we have, right? And so what we're going to do is we're going to use a mu, which is the population mean, right? And then on everything, I just put a little subscript diff, right? If I'm lazy, I'll just use a D, but I like to put the diff on there just to emphasize that it's the mean difference, right? So our point estimate is the average difference between the reading and the writing scores of the sample, which is X bar, and then a little diff on there tells me that it's the mean of the differences. Okay? And so we analyze the differences. This might be a good time to bring in our formula sheet. So here we were at one sample mean. We just recapped that, so that's good because we go, look at us zip through this formula sheet. It's crazy. You're doing it. I told you we'd go through it together. So I've got this paired data. Sometimes I call them matched pairs just to emphasize that, you know, they're matched on each observation. Whatever you want to call them is fine. I also have a note that we're analyzing the mean difference, right? So we want to learn about the mean difference. So we can make a confidence interval for the population mean difference. Sample mean difference plus minus T star at n diff minus 1 degrees of freedom, right? And so here our degrees of freedom is the number of differences minus 1. That can be kind of confusing as you're starting. How many differences do I have? I have 200, right? So even though I have a sample of the reading and a sample of the writing, right? Don't let that bog you down. In fact, once you have the differences, you can pretend that this doesn't even exist anymore. It does, but you can delete it, right? And so that's kind of nice. Maybe I shouldn't do it so harsh there. So I have 200 differences in this case, and that's my n diff. So everything just has a little diff on here, and everything stays the same, S diff over the square root of n diff, right? And so as long as we have all that same information, then we can make a confidence interval. So the same information that we needed for our one sample mean, hey, what? Here. One sample mean, we need that again, just of the differences. Now, of course, I'm not going to make you calculate that on the test. I'll give it to you usually in a table form or in word form. Okay, that's better, I guess. For doing a hypothesis test for the population mean difference, we first have to think back to our null hypothesis. Our null hypothesis has to be that nothing has changed, right? Until I have proof otherwise. And so going back to here, right? If I want to talk about the reading and the writing scores, I know I just crossed them out. If I want to talk about, okay, how are the reading and the writing scores comparing to each other? I want to know if there's a difference between the two. So that means that my null hypothesis has to be that there's no difference between them, right? No difference between the reading score and the writing score. What would that mean here? It would mean that the overall mean should be 0 if there's no difference, right? And so what's really nice is once you've decided that you have paired data, then this is always your null hypothesis. How does mu diff compare to 0, right? We have to assume it's 0 until I have proof otherwise. And so I'll highlight that because that's the only difference here. For paired data, H naught is always H naught is mu diff equal to 0. I want to see that diff on there because that tells me that you know that it's about the differences. And it's on your formula sheet, so I don't think it's asking too much. We're used to having to find a value to compare things to, but here we're only interested in, well, is there a difference in the two groups? We're still analyzing the two groups, but in a special way. Okay, and so then my alternative hypothesis can become a little bit trickier, right? Because it depends on how I calculated the difference, right? And so we saw in our difference here, I get a difference greater than 0 if the reading is higher than the writing score by how I calculated the difference. If I did it the other way around, then if the reading score is higher than the writing score, I would get a negative difference, less than 0. And that would be in my alternative. Because that's very, very tricky, I like to just do two-sided tests, right? Is there a difference in the reading and the writing scores, right? And so I'll do that on the test. I think maybe on an assignment or something like that, I have a one-sided test where you have time to think about it. And once you kind of have seen it a few times, it's fine. But the alternative will have a not equal to, right? And that's easier. A two-sided test. But then our t, well, our t is x bar of the differences. So our sample mean of the differences, how far is that from 0, right? Because that's my hypothesized value always. So I don't even write that down, but it's on your formula sheet. And then divided by the standard deviation of the differences over the square root of the number of the differences. And then, of course, again, the degrees of freedom is the number of the differences minus 1. Okay. So here it just goes through and talks about why it's 0. And it's because if, in fact, there was no difference between the scores, we would expect the average difference to be 0. And so this leads us to our hypotheses. Now, I have no clue where this came from. I should have caught it, I guess, but I didn't. If we want to test if there's a difference, and that's usually what I'll do, even if it makes more sense to test one side or the other, this makes our work easier. All right. I want to know if they're not equal to each other. Then the mean difference would not be 0, something else. Besides that, there's really nothing new here, right? Then we can just talk about one sample mean of the differences. And instead of this here, the independence condition we have to assume that our observations are independent of each other. And by that, we mean the observations, the students that we collected have to be independent of each other. One of the things in paired data is that we're actually assuming that between samples is not independent. In fact, they're dependent because they're paired, right? And so we're only concerned about independence within, okay? And so here, since the students are sampled randomly, and then I ignore this one, but you can say it if you want, and it's less than 10% of the population, right? Then we can assume that the difference between the reading and the writing scores are independent of one another. I'm going to add the normality condition down here. Since they didn't do it. Since n is equal to, or maybe I'll say n diff. Oops. Is equal to 200 is more than 30, we can assume normality, right? Once we reach 30, it doesn't really matter. The normality condition is satisfied. If we have less than 30, that's when we would look at the histogram and say, and argue it looks approximately normal. So we can assume normality. Okay. Instead of having the answers right there, let me just add a page here and just grab the question that we want to do. So sometimes I'll give you the information like this in a blurb, or sometimes I'll give it in a table where I include information on the reading and the writing scores, as well as the differences. I'd only give you information on the differences if they're what you're supposed to analyze. Okay. And so, oh, this I completely forgot, but did I make it available? I posted it. I might not have made it available. I posted a practice for test 2. Uh-oh, where is it? Here it is. It's hidden. Okay, let me fix it right away. Whoa. I'll move it into this week, but I want to show it. It's practice 4 test 2 because it's quite long. Obviously, it's not how much I expect you to do. Be very impressive. And just an outline of what to expect on test 2. I'm not going to test all of these, but this is what I need you to be prepared for. So 1 sample proportion, 2 sample proportions. Oh, and remind me, I think I said the sample size calculation was going to be a bonus. Did I say that? I think so. Anyways, it is. 2 sample proportions, chi-squared goodness of fit, 1 sample mean, which we just did last day, and then paired numerical data, which is what we're doing today, and then I draw the line. So we'll introduce 2 independent sample means on Tuesday, but it's not on the test because that would be rude. Okay. And so here's lots of problems. Now, what I want you to do, because it's a very important skill to have, is before you even try any of these, just go through and determine what type of question it is, right? What type of all of these is it, right? That's going to be a very important skill, okay? Not just for this test, but absolutely on the final exam, okay? And then the solutions that I'll post, they use the Z table, so I have to adjust it to use the T table. But besides that, I'll post the solutions, and then you can check against that, make sure you're on the right track. Okay. And wait. That's good. Can't believe I forgot that. There we go. So the observed average difference. Okay. So now this tells me that it's a mean difference between the 2 scores is negative 0.545 points. And the standard deviation of the difference is 8.887 points. Do these data provide convincing evidence of a difference between the average scores on the two exams? And we're going to use an alpha level of 0.05, which is the default anyways. Okay, so here we go. First, let's outline the information that we have. X bar is negative 0.545. Oh, whoops, X bar diff. Throw a little diff on there. S diff is 8.887. And we know from before N diff is 200. 3 pieces of information that we need for a means question. Okay. Anytime it says, do these data provide convincing evidence? Anytime you need evidence, you have to do a full hypothesis test. So here we go. Step 1, state the hypotheses. You don't have to list the steps. You do have to do all the steps, right? But you don't have to list them like I do. I list them to show you that we're doing the same thing always, right? And so it's up to you. I find that it's helpful, but we know once I've identified it as a paired data question, well, then I'm on easy street. Mu diff is equal to 0, right? And then, well, I already told you that it'll be mu diff not equal to 0, but we'll confirm why. Is there evidence of a difference, right? So then we have not equal to each other or not equal to 0. This is what makes it a two-sided test, right? I'm not concerned about just one direction. I'm concerned about both directions, both tails. And so this makes it a two-sided test, which means I'm going to need a two-sided p-value when the time comes. Okay. For the conditions, I'll just quickly check them here. Independence. The students were randomly sampled. And normality. N is greater than 30. So we assume normality. I just wrote that. That's why I'm zipping through it. Now we can go through and do our test. Step 2 is do the test, do the do. Do the test is really calculate the test statistic, which is T is equal to X bar diff minus, well, technically mu diff, but minus 0, because we assume the null hypothesis is true, which says mu diff is equal to 0 until I have proof otherwise, divided by S diff over root N diff. Have all those components. So here we go. Negative 0.545 minus 0, which I'll probably drop. 8.887 divided by the square root of 200. I have that calculated already here, I think. Uh-oh. I lost it. We have a T of negative 0.867. I need at least 3 decimal places because the table has 3 decimal places. So you might kind of mess things up if you round too soon. Your always welcome to keep more, but we need at least 3 decimal places. So t is roughly negative 0.867 to 3 decimal places. Gonna need a page. Uh-oh. That's very close to 0, right? We use the same kind of mental threshold of 2 for a t because we have large degrees of freedom. So they're very similar to the z. And so I know I'm not going to reject h naught, but the problem is this is hard to communicate to a client, right? And so we need p-values or probabilities to communicate the same thing. So step 3 is find the p-value. We use the same setup that we had for the z's, right, to find the p-value using the t-table. I just need the degrees of freedom first. And so what I like to see is if you tell me exactly what you're doing using the t-table, no harm in saying that, using the t-table with degrees of freedom equal to n diff minus 1, throw that diff on there, which is 200 minus 1, which is 199. We already know that there is no 199 on our table. Using software there is, of course, but we won't have that. Oh, delete that. So then I'm down here. Bring it in. Wait. So here, after this 199, you're going to tell me what it should be, and then tell me what you're using, but using if the exact one isn't on there. So we're going to be between 100 and 1,000. Of course, we have to bump it down to 100. Otherwise, we're lying. Right. But using degrees of freedom equal to 100. This tells me a lot of things, right? It tells me that you know to use the t-table. That's a good start. Kind of a freebie. Tells me that you know how to find your degrees of freedom. It also tells me that you know to round down, right? It's 3 pieces of things. 3 pieces of things. Well, so now using the t-table, I guess not period yet, we find, and this is where we use the same setup, right? The absolute value of the t that we calculated goes in the center. So I'm going to write that out here. T is equal to negative 0.867. Oops. Is between 2 values. I like to do my setup first, and then it's more of a fill in the blank situation, right? And so here, once I have my t, the values that surround my t, then I have my p-value. But I'm not going to stop there. I'm going to showcase that I know I have a one-sided or a two-sided p-value. Let's just remind ourselves that's from here, right? I'm interested in a difference, so either direction. So I have a two-sided test, so I need a two-sided p-value. So the two-sided p-value is also between 2 values. I don't like to think about inequalities, and it always trips me up when I have students who switch the signs. I have to spend so long thinking about it. You could, right? Then you can list them as they appear, but it's confusing to me, but that's all right. I can handle it, I think. On the 100 degrees of freedom line, this t, right, the absolute value drops the negative, so it's somewhere between 0.8 0.045 and 1.042. From there, I have, oops, this looks like I'm going to the one-sided P. I need a two-sided P. And it's somewhere between 0.3 and 0.4, right? You have to read these from right to left if you use your inequalities like I do. And that's just because as you move further out into the tails, then the area in the tail gets smaller and smaller. This is quite large though, right? Which confirms what we found earlier, kind of gut reaction. Oh, I'm probably not going to reject H naught because this T is very close to 0, right? It's not past 2 standard errors away. So now, conclusion time, hardest part. Usually it's 3 out of 8 marks on a hypothesis testing question. As long as you follow through. I know I've mentioned it before, but if you're completely stumped on your p-value, just tell me a reasonable value for your p-value, right? Even if it's wrong, right? P-values are probabilities, so they have to be between 0 and 1. That's your first kind of reasonable part. And they should be kind of on the lower end, right, in the tails. And so just remember that. And then as long as your conclusion follows what you told me you were going to use, I can't complain, or I won't complain, rather. Your conclusion. We follow the same setup as before, right? We show off all the things that we know, right? All the things that we're thinking about go into the sentence. What are we thinking about? Well, I'm comparing my p-value to my alpha level. We were told to use 0.05. Neither of these are less than 0.05, and so our p-value is not less than 0.05. So we say, since our two-sided p-value is between 0.30 and 0.40, right? No harm in saying what it is. And I want to see that. Okay, I will warn you that I will mark you up hard on test 2, as hard as I can, because then I can be more lenient on the final exam and kind of steer up any kind of mistakes that you're making. Okay, and so I'll be a little bit harsh, but you'll learn some lessons. Okay, and so there, said it. But then you'll be on easy street for the final exam, I promise. Because then there's no more lessons to learn. So since our two-sided p-value is between 0.3 and 0.4, it is not less than alpha equal to 0.05, which means we do not have enough evidence to reject H naught. Which means we do not have enough evidence to reject H naught. Oops. That conclusion always has to be in terms of H naught, right? You either have enough evidence to reject H naught or you don't, because we did all our testing assuming that H naught was true until I found proof otherwise, right? And so it has to be in terms of H naught. And so we don't have enough evidence to reject H naught, which means what? In terms of the question, well, that's where we steal. This is the only time where the conclusion becomes question specific. Lesson. Copy. Oops. Paste image. Therefore, these data do not provide convincing evidence of a difference between the average scores on the two exams, period. Okay. Good. I'm lazy, so I'm not going to write that out. But tough. You can't have copy paste on your test to write it out. Okay. Good. Tedious, yes, but not hard once you get the dance. All right. They squeezed all that into one slide somehow. Gonna zip through it. They didn't state their null and alternative hypotheses or anything, but what they did is they used software at 199 degrees of freedom, and they found that the p-value is actually 0.3854, which is between 0.3 and 0.4. Fair enough, right? And so we could find it. I think I mentioned it already, but who knows? On the assignments, you have to use the same degrees of freedom as you used in the table, because otherwise they might be just a little bit off, but that's okay when you use software, which you won't have to use on the test, obviously, because it's on paper. Okay. Oh, I don't like this slide, but you can read it because I know the p-value is kind of tricky, but I find that it can be kind of confusing, this one, so you're welcome to read it if you'd like. But I want to do this one. I've already briefly mentioned that, okay, I can use a confidence interval to test the hypothesis, at least informally, right? And how would we do that? We say that if the null value is inside the interval, right, then there's no reason to reject H0. It's one of the plausible values in my confidence interval. I'm 95% confident that it's capturing the true population mean, for example, mean difference maybe. And so if the null value, and so here H0 is that mu diff is equal to 0, this 0 is the null value, right, from the null hypothesis. If the null value is in the interval, right, then you don't have enough evidence to reject H0. If the null value is in the confidence interval, right, 95, 99, whatever, they're usually high percentages. So if the null value is in the confidence interval, we do not have enough evidence to reject H0. It's kind of neat. We could flip it. We could say, okay, in this case, we didn't have enough evidence to reject H0. So then, would I expect this interval to include 0? Yes, I would. Okay. And what I want to do is I want to make the confidence interval together. Put it here. Just to see it. Ah, perfect timing. Okay. So if I want to make a 95% confidence interval for the mean difference, well, we're going to use X bar diff plus minus T star at N diff minus 1 degrees of freedom times S diff over root N diff. X bar diff I have from before is negative 0.545 plus minus T star at 100 degrees of freedom. Let's see, where's that little table? I think maybe we're grown up enough for me to just show you on the table and not do a screenshot because it's kind of annoying. I want a 95% confidence interval, which means here. And we already worked out the degrees of freedom that we're going to use is 100. So then our T star is 1.984. Come on. T star is 1.984. 1.984 times 8.887 divided by the square root of 200. And I have that here. Oops. So again, plus minus chunk is my margin of error, which I called M. And then I subtracted M and I added M. And I found that the interval for the mean difference was between negative 1.79, let's just go 2 decimal places, 2.70. Yeah, that's for the difference, right? The average difference. Interpreting this, or maybe we'll see here, on a number line, I'm 95% confident that somewhere between negative 1.79 and 0.70, I've captured the true population mean difference. Well, zero's in here, so it's one of the options, and that's why I don't have enough evidence to reject H0. Now, if the entire interval was negative, I would reject H0, or if it was positive, I would reject H0, but because zero's in there, I don't. We are, I know you wanted to forget about the interpretation, 95% confident. The interval from negative 1.79 to 0.70 captures the mean difference, but it'll also be in the question, right? The average difference, but I'll say mean just to emphasize that it's a means type of question. And so the average difference or the mean difference between the reading and the writing scores captures the mean, I'll put in brackets, the average difference, right? That's what we're analyzing between the reading and writing scores. All right. They did the calculation, but not the interpretation, but I want to see the interpretation, of course. Test number 2 is up to here. Up to here. And then we'll start the difference in 2 means next day. If you have any questions, let me know. Otherwise, enjoy your weekend.